Let's have our lecture in Geotechnical Engineering with the topic Lateral Earth Pressure. Now in this video, we will discuss some of the principles in solving lateral earth pressure by solving our sample problems there in our study guide. Now, retaining structures such as retaining walls, basement walls, and bulkheads commonly are encountered in foundation engineering as they support slopes of earth passes. Proper design and construction of these structures require a thorough knowledge of the lateral forces that act between the retaining structures and the soil masses being retained. These lateral forces are caused by lateral earth pressure. The magnitude and distribution of lateral earth pressure depends on many factors, such as the shear strength parameters of the soil being retained, the inclination of the surface of the backfill. So we will also have formulas considering the inclination of the backfill, the height and inclination of the retaining wall at the wall backfill interface, the nature of wall movement under lateral pressure, and the adhesion and friction angle at the wall backfill interface. Now we have two coefficients to consider. We have the active earth pressure coefficient and the passive earth pressure coefficient. Now the difference between the two is that the active earth pressure coefficient, K sub A, is the ratio between the lateral and vertical principal effective stresses when an earth retaining structure moves away by a small amount from a retained soil. For passive earth pressure coefficient, or K sub P, it is the ratio between the lateral and vertical principal effective stresses when an earth retaining structure is forced against a soil mass. So to illustrate, if this is the if this is the structure, for example, a concrete retaining wall, and then you have here a soil mass. So at this right side here, that is the soil being retained. So the active earth pressure coefficient is used to calculate the force that makes the structure to move away from the soil it is retaining. So it is in short, we can imagine it as the force that pushes it or pushes the structure away from the soil it is retaining. Whereas the passive earth pressure, it is the force that will push the structure against a soil mass. Okay, so this is the active, and this is the passive. So the active forces will destroy the structure because it will push away. Okay, so it will make it they call that, it will move away from the soil being retained, whereas passive will help hold the soil. So this is more destructive and this is more constructive. Okay, so these are the formulas that we are going to consider. We have two formulas to use. We have the Rankines and the Coulomb's. So Coulomb's coefficient, how we can remember it is that it's more lengthy. So if you can observe, it has more parameters compared with the Rankines coefficient. So we're going to use the Rankines and the Coulomb's. But in these sample problems that I have in your study guide, we are mostly using the Rankines coefficient. In the problem, if it is not mentioned, use Rankine. Okay? Unless Coulomb is mentioned. So again, if in the problem it wasn't mentioned what coefficient to use, then it's automatic use Rankine. Okay, so these are the formulas. So we have formulas at rest. We have formulas horizontal and vertical, horizontal and inclined. We have also the columns coefficient, right? So let's go to the the active pressures on the wall and the passive pressures on the wall. So you can see all these formulas here. These can be derived by using the diagrams. So let's see how these formulas have been derived based from these diagrams. So for example, here in active pressure on wall, we have to get the formulas for the force due to cohesion, due to surcharge, due to soil, and due to water. Okay, so we have here the diagram. So this is the structure. Okay, so again, so this is the structure here, concrete structure. Let's say that's a retaining wall. This is the soil that is being retained, and that soil sorry, is experiencing surcharge Q in kilopascal. Okay, and in this soil being retained, we have two types of soil. The clue there being the phi here. Okay, so we have two different kinds of soil in this figure. And let's get the formula for cohesion. So as you can see, you have diagrams for cohesion. So cohesion, surcharge, soil, and water. Because of the presence of water here, here is the water table. Okay, so these are the forces that causes the structure to collapse. Okay, so these are the passive force these are the active, so active forces. So the active forces due to surcharge, of course, it will have an effect to push the structure away from the retained soil. We have the water, so we have here the water, it has the force also. The soil itself, so the soil has a contribution to push the wall away. Now here is the question, why is the cohesion here? Why is the cohesion in a different direction? Okay, so instead of going to the left, or instead of pushing the retaining wall, it instead it's in the opposite direction. So when we say cohesion, the cohesion will tend to make the structure stick to the soil mass. Because of the presence of cohesion, instead of the structure to be pushed away, it tends to stick to the soil mass. So in this side of the diagram, so we are considering the soil here. What we will do is, since cohesion is in a different direction, we will deduct the force of cohesion. So here, if we put positive to the left, the sign for cohesion here is negative. The sign for surcharge is positive, soil is positive, and then water is positive. Okay, so that's how we will analyze this diagram. Okay, so now let's get the formulas based from these diagrams. So also we observe that for cohesion, the distribution of load is uniformly distributed. For surcharge, it's also uniformly distributed. for soil, it is uniformly varying, and then for water, also uniformly varying. Okay. Let's go to the first. If we are considering here active pressure on retaining wall, of course, the first thing we do is we compute for the K active. Okay. Again, if in the problem it's not mentioned whether to use Rankine or Coulomb, therefore you will use the Rankine coefficient. So for Rankine coefficient, we have K active is equal to 1 minus sine of phi over 1 plus sine of phi. Okay. Now for the first type of soil on the upper portion here, obviously we have a different K active. So K active 1, we will use phi 1. For K active 2, we will use, of course, sine phi sub 2, 1 plus sine phi sub 2. Okay, so that's for the K active. Now let's go to the cohesion. To get the force because of cohesion, let's get first the pressure. Okay, we will start at the top. So the P cohesion 1 is equal to, the formula for cohesion actually is PC equals 2C square root of 2K, active or passive. Okay, that's the formula for cohesion. So for the upper portion, upper one here, upper soil. Okay, so we have 2. So the value for cohesion 1, so you can see we have here cohesion 1 square root of K active 1. Okay, so that's for cohesion. And then the force for cohesion 1 is equal to the, it's actually the volume of this, but we will take this as per meter width. So it will be PC1 times the height 1. Okay, so that's for cohesion. Let's go to the second soil. We have PC2, then 2C sub 2 square root of the K active 2, of course, because it's a different soil now. Then the force here, FC2, is equal to PC2H2. Okay. So basically in the diagram, it's the area. Okay. So that's for cohesion. Now let's go to the surcharge. For surcharge, it's also uniformly distributed load. Okay, so the upper soil there, we have there for P sub 1. Okay, getting the pressure for surcharge, P sub 1 is K active 1 gamma the top, then the height of the upper soil. Then we have there the force now for the upper soil due to surcharge is now equal to, no, I'm sorry, so this is different. Okay, the formula for surcharge is different. What I'm doing is the soil. Okay. So for surcharge, we have P sub 1 equals K active. Okay, K active 1. And the surcharge is given as Q in kilopascal. So that is Q. Okay, and then force 1 is now equal to the area. We have the P1, then H1. Then for the lower part of the soil, we have there P sub 2, then we have K active 2, then Q. Q being the surcharge, and then we have there the force due to surcharge. Okay, we have there the area. We have P sub 2, H sub 2. Okay, so that's for the cohesion and surcharge. Let's go to the soil, which is I'm doing a while ago. Forgot. Now let's go to the soil. This time we are looking at this diagram here. Okay. This diagram here. For the soil, we have the formula for P pressure 3. So pressure 3 here. P3, P4, P5. Now, we will explain why there is a presence of P4 here. We know that for soil, we are considering uniformly varying load. So that's why we have here a uniformly varying for the upper soil. So P3 is K active 1, gamma 1, and then H1. And the force here is equal to 1/2 the base times the height. Okay, so that's for the upper soil. Let's go to the lower soil here. Now, observe that there is P sub 4 uniformly varying, uniformly distributed, plus a uniformly varying load. Okay, so P sub 4 is uniformly distributed, P sub 5 is uniformly varying. Why? Now, this is a special case. This happens when there is two different soil types here, and it's being divided by the water table. There's a water table here. Okay, for the special case P4, this is special. You will put here P4. Why special? Because take note, it's at the lower part. That's why it's obvious this is K active 2. Okay, but we will get the gamma 1 H1. Okay, again for P sub 4, special case here for the soil is that we have K active 2 and then multiplied with gamma 1 H1 from the top. Okay, so that's for P4. That's why you will get F4 now equals, of course, the area. We have P4 H2. Then let's go to the uniformly varying P5. It's not done yet. So let's go to P5. And that is K active 2, gamma 2, H2. So this is now the one below. But this gamma here, gamma 2 here, it's not just gamma 2. Rather, you have to take the gamma buoyant 2, H2. Why gamma buoyant? Gamma effective. Because we separated the water. The water is already here. Okay? So, we are concentrating only soil here. So, we need to remove the water. Gamma here is gamma sat. So, we need to find the gamma effective. So, we will be using gamma effective or gamma buoyant for P sub 5. And then for the force 5, we now have 1/2 of P sub 5 H2. Next, let's go to water. Okay, the force of water. But first we will get the pressure. Pressure here for water, so P6 or P water. You can just put P water. That is gamma of water times the height. So for the force of water, we have there 1/2 base times height. Okay. So that's for the forces for soil and water. Now, if we're looking for the total active forces, so total active forces FA, that is now equal to, we have a negative FC1, negative FC2. Okay. And then we now have positive F, positive force 1, positive force 2, positive force 3, positive force 4, positive force 5, and then positive force of water. So that's the total active force. And then for total active moment, well, you just have to find the distance of the forces from the heel or from the bottom of the structure. So that's because the rotation, the movement for the structure, if it's going to fall down, is that this is the rotation point, the heel. Okay, so the force, the distance of the force should start from the heel, so from the bottom up to the force. Okay, so we have here moment, total active moment M sub A is equal to negative FC1 times YC1 minus FC2 YC2 plus F1 Y1 plus F2 Y2 plus F3 Y3 plus F4 Y4 plus F5 Y5 plus F water Y of water, or in the diagram that is F6. Okay, so that's how we get the formulas here in our study guide. Okay, these are the formulas. Now let's go to the passive pressure on the wall. So let's consider also the passive pressures. Okay, so here it is. So again, this is the structure that we have considered a while ago. So this is the structure. This is the same structure here. And then we are going to consider this side of the structure for the passive action. Now, why passive action? Because we are going to see the force exerted by this fill here, for this at a certain height h. Right, so let's start with the coefficient. So K passive coefficient, that is 1 plus sine phi over 1 minus sine phi, or basically that is inverse of K active. So that's just the inverse of K active. Okay, so let's go first to the cohesion. Again, for passive forces, since its job is to make the structure stable, so it is pushing the structure against the the soil, it is retaining. So that is the passive forces. So passive. So these are the passive forces here. Therefore, all of this here, cohesion, soil, and water, helps in retaining the soil there. It helps in pushing the structure to retain the soil. Therefore, these are all positive. Okay, positive to the right. Okay. So let's start with cohesion. So for cohesion, we have their PC. So PC, so this one here, cohesion. So that is 2C square root of K passive. So that's the pressure for cohesion. Then this is the force for cohesion. We have the area, PC times H. Okay, so this should be C. Next, we have the soil. For the soil, we have here pressure 2. So in the diagram, it's pressure 2. Okay. So we have K passive, then gamma. Since this is water, so it means the soil is saturated. Therefore, what we will do here is we will take the effective gamma or gamma buoyant. Then we have H. Then for force of soil, we now have 1/2 base times height. Lastly, we have the water. Water, pressure of water there, P sub 3, is equal to gamma water H. And then for the force of water, we have 1/2 base, which is P sub 3, and then the height. Okay? And we now have the total passive resistance, FP, passive forces. We have FC plus F2 of the soil plus F of water. Then passive moments, total passive moments, or total passive moment is FC times the Y1 there plus F2 Y2 plus F3 Y3. Okay, so that's how we got the formulas in this study guide. Right, so I think we're ready to solve the different sample problems in our lecture video. Now, in this lecture video, we will answer the 2 sample problems there in your study guide. And in the next lecture video, we will answer the remaining 3 sample problems. Okay, so let's start with number 1. So we have a retaining wall, 8 meters high, and it is supporting a horizontal backfill having a dry unit weight of 1600 kg per cubic meter. The cohesionless soil has an angle of friction 33 degrees. Letter A, compute the Rankine active force on the wall. B, compute the Rankine active force on the wall if the water table is located at a depth of 3.5 meters below the ground surface. So, it's a different scenario. The first one, it's just plain soil. The second one, there is water table located 3.5 meters below the ground surface. And of course, if there is a water table, we have saturated unit weight. which is 18.7 kilonewton per cubic meter. Then letter C, compute the location of the resultant active force from the bottom for the second condition. Okay, so let's start to solve this. This problem does not contain a picture, but so this is the structure. So 8-meter high wall. Okay, so let's have the so the given is gamma D, gamma dry, 1600 kilogram per cubic meter. We have its cohesion less, so C is equal to 0. The angle of friction is phi equals 33 degrees. So the first thing we will do here is compute the coefficient. So the problem already mentioned Rankine, so we will use Rankine's active coefficient, 1 minus sine phi all over 1 plus sine phi. So 1 minus sine of 33 degrees all over 1 plus sine of 33. So K active now is equal to 0.295. 0.295. Then what we have here is gamma D. So dry unit weight, but the unit is kilogram per cubic meter, so it's a density. So for unit weight, we have rho G. Okay, so rho G is 1600 kilogram per cubic meter multiplied with 9.81 meter per second squared. So what we got here is 15,696 kilonewton per cubic meter. That's Newton. That's Newton per cubic meter. So gamma is equal to 15.696 kilonewton per cubic meter. Then we will use that gamma. Again, let's see, does this have cohesion? No, this doesn't have cohesion. Surcharge. Oh, soil. Of course, it has soil. So let's have here the uniformly varying soil. Then this is the pressure for the soil, and then this is the force. Since it is active, the motion of the force is it tends to push the structure away from the soil. Okay, so we get the formula for soil. P, the pressure for the soil is K active gamma H. So K active is 0.295, gamma is 15.696, and then the height is 8. So pressure now is equal to, so that is 37.04 kilopascal. Then force now is equal to 1/2 base times the height, 8. Force is equal to 148.16 kilonewton per meter width, or let's just say per meter. Okay, so that's for letter A. Compute the Rankine active force on the wall. Now let's go to letter B. The letter B is a different scenario or it's a second condition. It has water table at a depth of 3.5 meters below the ground surface. Okay, so for letter B, there is the presence of water table here. Okay. So that is 3.5 meters. And then this is 4 meters. And then it has a gamma sat of the gamma sat here is 18.7. Okay, so 18.7. So does this have cohesion? Again, no. How about soil? Yes, we have soil. Let's draw the soil diagram for the soil. Okay, for the soil, let's take the first uniformly varying here. Let's name that as P sub 1. Okay. So P sub 1 is equal to K active, then gamma H, or this should be gamma 1 H1. Why? Because we have a different gamma. So K active is still 0.295. Okay, let's put it here. 0.295. The gamma is 15.696. The height is 3.5. P sub 1 is equal to 16.21 kilopascal. Now let's proceed to the P sub 2. At P sub 2, is this a special condition because of the presence of water table? No, it's not a special condition because the phi here is the same as here. Okay, therefore the next one will be another uniformly varying. Okay, so there you go. This is going to be another uniformly varying. This is our P sub 2. Okay, so P sub 2 is equal to still K active is the same because it's the same soil, 0.295. So 0.295. I think I should be writing it as K active and then gamma buoyant, then H2. And that is equal to 0.295 times gamma buoyant is the gamma sat 18.7 minus 9.81. Then H sub 2 is 4. That is now equal to 11.8 kilopascal. Okay, so that's for the soil. Let's go to the water. So water, so this is for the water, it's uniformly varying also. P water. P water is equal to gamma H, or gamma water, then H2. So 9.81 times 4. 9.81 times 4.5. Should be 4.5. Therefore, this should be 4.5 here. That is equal to 44.145 kilopascal. Okay. So we're done with the pressure. Let's go to the forces. Okay. So we have here the force. So this is the F1. Let me use a different color for the forces. Let's say, let's use green. Okay, so these are the forces existing here. So this is F1, this is F2, no, this is, yeah, okay. So let's put that as F3, because this is F2. F3, F2. Then this is F of water. Now we finally have our forces, F1. Our F1 is 1/2 base times height. So 1/2, our P1 is 16.21 times the height 1 is 3.5 meters. So F1 is equal to 28.37 kilonewton. And we have there F2. F2 is 1/2 P2 H2. So 1/2 of P2, which is 11.8 kilopascal, then H2 4.5, 26.55 kilonewton. Then let's go to F3. F3 is the rectangle here. So F3 is P1 H2. So P1 being is 16.21 times 4.5. That is equal to 72.945 kilonewton. Then finally we have the water. Force for water, we have 1/2 base times the height equals 1/2 of P water, that is 44.145 times H2 being 4.5. We now have 99.326 kilonewton. Now, what is being asked again, the problem? What is being asked? It says there, compute the Rankine active force. Okay. The Rankine active force, FA. So, FA is now equal to the total. So, we have F1 plus the F2 plus the F3 plus the F water. So, 28.37 plus 26.55 plus 72.945 plus 99.326. That's all equal to 227.19 kilonewton. And that is in per meter width. Now, letter C, what's being asked in letter C? Compute the location of the resultant active force. It's looking for Y bar, or so from the bottom for the second condition. Okay, so for Y bar, let's use yellow. So this is Y1 for F1. Let's arrange them. This is Y1, Y3, let's say that's Y3, this is Y2, YW, Y1, Y3, Y2, and then this is YW. Okay, the location for Y1 is 4.5 plus, okay, that is 4.5 plus 1/3 of 3.5. Okay, so that's Y1. Y2 is 1/3 of 4.5. Y3 is 4.5 divided by 2. And Y water is 1/3 of 4.5. Okay, so let's write that down here. Letter C. So Y1 is 4.5 plus 1/3 of 3.5. Y2 is 1/3 of 4.5. Y3 is 1/2 of 4.5. Then Y water is equal to 1/3 of 4.5. So Y1 is 5.67 meters. Y2 is 1.5 meter. Y3 is 2.25 meters. Y4 is 1.5 meter. Now for that, we have a total of 227.19. Y bar is equal to 28 point. So this is F1. So it's best if we just show what's happening here. FA Y bar is equal to F1 Y1, F2 Y2, F3, okay, let's see, so F3 Y3 plus F water Y water. So we have 227.19 Y bar equals 28.37 times 5.67 plus 26.55, 1.5 plus 72.945 times 2.25 plus 99.326 times 1.5. So Y bar now is equal to 2.26 meters. So that's for letter C. Okay, so that's all for number 1. Just screenshot first. Okay, now let's proceed to number 2. the last example for this video. A frictionless vertical retaining wall has a height of 4 meters and retains a horizontal surcharge of 10 kilopascal. So here is the horizontal surcharge. This is the structure. Okay. And this is the soil being retained. Unit weight of the backfill is 15 kilonewton per cubic meter. Okay, let's write that. Unit weight is equal to 15 kilonewton per cubic meter. Cohesion, 8 kilopascal. Angle of friction, 26 degrees. Letter A, compute the maximum depth. So the maximum depth of the tensile crack. Compute the active force after the tensile crack occurs. Compute the passive resistance per unit width of the wall. So the tensile crack. So the tendency for the crack to occur. Where in this structure will that crack occur? Okay, let's see. Let's analyze the structure. So there is the presence of cohesion. So let's just follow the arrangement from our study guide a while ago. So let's start with the cohesion. So this soil has cohesion. So uniformly distributed load for cohesion. Then we have surcharge. Surcharge is also uniformly distributed. So, okay, so this is let's put here surcharge. We have a very limited space. That's the surcharge. Then we have the soil. Soil is uniformly varying. Triangle. And there's no water here. Okay. So let's cohesion, surcharge, and soil. I'm going to show you a setup in order for you to be able to solve for the location of the tensile crack immediately. Okay. And then how do we orient the forces again? For the force of cohesion, it tends to stick. Okay, the structure tends to stick to the retained soil. So this is FC. So since it's contrary, so it's contrary to the action which is active, we will put here negative PC. Okay, so the pressure here is negative PC, negative force. Surcharge tends to push the structure away. So this is F1 positive. So positive P1. The soil has a tendency to push the structure away. So we're solving for active forces. This is positive also. Okay. Let's solve for the K active. So always looking for the K active. After all, it says there. Okay. Compute the active force later on. 1 minus sine phi, phi being 26, 1 plus sine of 26. So, K active is equal to 0.39. P sub C now is equal to 2C square root of Ka. That is equal to 2C is 8 kilopascal. Square root of K active, 0.39. So, P sub C is now equal to 9.99 kilopascal. Now, let's go to P1. P1 is equal to the surcharge. K active times Q, the surcharge. K active 0.39, surcharge is 10. Therefore, P1 is 3.9 kilopascal. P sub 2. P sub 2 is soil. Soil, and that is K active gamma H. So, K active 0.39. Gamma is 15. H is 4. That is equal to 23.4 kilopascal. Okay. Now, let's use all this pressure to create a diagram. Okay, so that is equal to, so at the top here, we have negative PC, positive P1, 0 P2. What is negative 9.99? Okay, so what happens here at the top is it's negative 9.99 plus P, P sub 1, 3.9. That is equal to 6.09. So that is equal to 6.09. Let's say it's located here. Negative. Okay. So that's negative 6.09. Whereas we have the bottom, we have negative PC plus P1 plus P2. Negative PC is negative 9.99 plus 3.9 plus 23.4. That is equal to positive 17.31. So that is positive 17.31. Thus, we have here a diagram that looks like this. Okay. And this is what we're going to use to solve for the tensile crack. Alright, so where do we find the tensile crack? So the tensile crack is located at where the intersection of the passive and active force is. So here it is. So this is the tensile crack. Let's name that as Z. Okay, so how do we find the location Z? Oh, by the way, where depth? Okay, so it says there maximum depth of the tensile crack. If we're talking about depth, of course, that means our reference point will be from the ground surface, not at the bottom of the structure, because the word there is depth. Okay. So we now have Z, and by using similar triangle theorem, we have there Z over 6.09 equals 4 minus z all over 17.31. Therefore, z now is equal to 1.04 meter. That's the location of the tensile graph. So that's for letter A. Let's go to letter B. Compute the active force after the tensile crack occurs. So how do we understand this? What is the active force after the tensile crack occurs? So since the tensile crack occurs, therefore this upper portion here is removed. Thus, our concentration will go at the portion here. Okay? So we will solve for the force here, and let's name that as FA prime. Let's name that as FA prime. So for letter B, what is FA prime? So FA prime is equal to 1/2 of 17.3 times 4 minus 1.04. Therefore, FA prime is now equal to 25.604 kilonewton per meter width. Okay? Per meter width. Why per meter width? Because it's in per meter width of the structure. Okay, let's go to letter C. Compute the passive resistance per unit width of the wall. Passive resistance. So what force can resist the destructive forces for the structure to fall? Okay, let's use another figure. Let's go to this one. Alright. So a while ago, we considered what are the force, the active force. Now this time, let's go to the passive force. So the question basically asks, what is FP here? The force that will resist. Okay, so basically FP, the summation of FP will be the summation of forces here. Okay, so whatever we solve here, the value of forces here will become the FP. Okay, so do we have cohesion? So let's put here gamma 15, cohesion is 8, then phi is 26. So yes, we have cohesion. Therefore, we have here cohesion diagram. Okay. Do we have soil? Of course, we have soil. But the orientation will be like this. Do we have surcharge? Yes, we have surcharge. Okay, I should put the soil here, because the surcharge should be here. Okay. Alright. So we can get the value for FP by solving for this one. So for FC, this is for surcharge F1. So this is cohesion. surcharge, and we have soil. So here goes our force 2, soil, right? So we have here P cohesion, P of surcharge, P of soil. And these are all positive. Positive, positive, positive. So since we are solving for passive forces, let's have K passive first, Kp. That is reciprocal of K active. 1 over 0.39. So K sub P is 2.56. P sub C now is equal to 2C square root of K passive. 2 times 8 square root of 2.56. That is equal to 25.6 kilopascal. Let's go to the surcharge, P sub 1. Surcharge is K passive Q. So K passive 2.56, Q is 10. And that is equal to 25.6 kilopascal. Then we have the P sub 2 for soil, and that is K passive gamma H. That is equal to 2.56, gamma of 15, H or height of 4. That is equal to 153.6 kilopascal. Okay, so having all these values of pressure, of course, we can get the FP now as the total, the summation of F. Also, we can use another means, we can have another method by using a diagram. Okay, so this is now equal to positive PC, positive P1. What is PC plus P1? What is 25 plus 25? That is 51.2. Okay, so this is now 51.2 kilopascal. Then for the lower part, what is PC plus P1 plus P2? That is 25.6 plus 25.6 plus 153.6 is equal to 204.8. Okay, so you now have this diagram here. Therefore, FP now is equal to 1/2 of 51.2 plus 204.8 times 4, and that is equal to 512 kilonewton. 512 kilonewton per meter width of the structure. Okay, so you can also use this means. You can have if you still have space here, you can have the singular diagram, or you can summation, find the total forces by doing summation of forces. So that's for letter C. So I should put here letter C. Okay, that's for number 2. Screenshot here. Okay, so that's all for this lecture video. This is the part 1 for lateral earth pressure. So stay tuned for the second part for the lateral earth pressure. We will answer 3 more sample problems.